Today we're going to explore one of the most important stories in thermodynamics. The ideal gas law, which scientists thought was universal, failed miserably under certain conditions. This failure led to one of the greatest insights in molecular physics. Let's start with the ideal gas law. This equation was developed in the 1800s, and it seemed to work wonderfully for many gases under normal conditions. PV equals nRT. Pressure times volume equals the number of moles times the gas constant times temperature. This elegant equation relates the four key properties of any gas. P is the pressure, which measures how hard the gas pushes on the walls of its container. V is the volume, the space the gas occupies. N is the number of moles, which tells us how many molecules we have. 1 mole is 6.02 times 10 to the 23 molecules. R is the universal gas constant, approximately 8.314 joules per mole Kelvin. It's the same for all gases. T is the absolute temperature in Kelvin. Remember, 0 Kelvin is absolute zero, the coldest possible temperature. But here's the critical question. What assumptions does the ideal gas law make? Understanding these assumptions is key to understanding where it fails. First, the ideal gas law assumes that gas molecules themselves have zero volume. They're treated as mathematical points with no size at all. Second, it assumes there are no intermolecular forces. Molecules don't attract each other, and they don't repel each other, except during instantaneous collisions. In the ideal model, molecules are like tiny billiard balls with no size, flying around randomly with no forces between them except when they collide. So when does the ideal gas law actually work? It works beautifully under certain conditions. It works well at high temperatures, typically above 300 Kelvin, or room temperature. At high temperatures, molecules move very fast. It also works well at low pressures, below about 10 atmospheres. At low pressures, molecules are far apart. Why do these conditions matter? When molecules are far apart and moving fast, the two assumptions become reasonable. The volume of the molecules is tiny compared to the space between them, and intermolecular forces are negligible. But engineers in the 1800s discovered something shocking. When they tried to compress gases to high pressures or cool them to low temperatures, the ideal gas law failed catastrophically. The first major problem appeared near the condensation temperature. This is the temperature where a gas turns into a liquid. According to the ideal gas law, as you cool a gas, it should continue to obey PV equals nRT all the way down to 0 Kelvin. Instead, something dramatic happens. The gas spontaneously transforms into a liquid at a specific temperature. The ideal gas law predicts nothing of the sort. Imagine cooling steam. At high temperature, it's a gas with molecules far apart. But at 100 degrees Celsius, it suddenly condenses into liquid water. The ideal gas law cannot predict this phase transition. For water, condensation occurs at 373 Kelvin or 100 Celsius at 1 atmosphere pressure. The second major problem appeared during high compression experiments. Engineers tried to compress gases to very high pressures. The ideal gas law predicts that volume should be inversely proportional to pressure. Double the pressure, halve the volume. Simple. But reality was different. At moderate pressures, gases compress more easily than the ideal law predicted. The volume decreased faster than expected. Then, at very high pressures, the opposite happened. The gas suddenly resisted further compression much more strongly than predicted. It became almost incompressible, like a liquid. Imagine compressing gas in a cylinder. At first, it compresses easily. But then the molecules get so close together that their finite size matters. You can't compress them any further without enormous force. Engineers catalog these deviations systematically using something called the compressibility factor, represented by the letter Z. Z equals PV divided by nRT. For an ideal gas, Z always equals 1. Any deviation from 1 indicates non-ideal behavior. When Z equals 1, the gas is behaving ideally. The ideal gas law works perfectly. When Z is less than 1, the gas compresses more easily than predicted. This happens at moderate pressures where attractive forces dominate. When Z is greater than 1, the gas resists compression more than predicted. This happens at very high pressures where molecular volume dominates. Let's look at real experimental data for nitrogen gas at 300 Kelvin. This data shows the dramatic failures of the ideal gas law. At 1 atmosphere, Z is 0.999, nearly perfect. At 50 atmospheres, Z drops to 0.98. The gas compresses more easily due to intermolecular attractions. At 200 atmospheres, Z is 0.85, a huge deviation. But at 500 atmospheres, Z jumps above 1. Now molecular volume dominates, and the gas resists compression. At 1,000 atmospheres, Z is 1.9. The gas is almost incompressible. So what's really going on? Why does the ideal gas law fail so dramatically? The answer lies in two physical facts that the ideal model ignores. The first physical fact is that molecules do attract each other through intermolecular forces. These are called van der Waals forces. They're much weaker than chemical bonds, but they're real and measurable. When molecules get close together, they pull on each other. This attraction makes the gas easier to compress than the ideal law predicts. Picture two molecules approaching each other. They experience a weak attractive force that pulls them together. This is why gases can condense into liquids. This attractive force explains why Z is less than 1 at moderate pressures. The attractions help pull the molecules together, making compression easier. The second physical fact is that molecules are not mathematical points. They have real, finite size. Each molecule occupies a tiny but definite volume. For nitrogen, each molecule has a diameter of about 3.6 angstroms. 1 angstrom equals 10 to the negative 10 meters. It's incredibly small, but it's not zero. At very high pressures, molecules get packed so tightly together that their size becomes important. They literally run out of room. When molecules are packed this tightly, you can't compress the gas any further without crushing the molecules themselves. This is why gases become nearly incompressible at very high pressure. This finite molecular volume explains why Z is greater than 1 at very high pressures. The available free space is much less than the total container volume. For decades, engineers collected data on these deviations, but nobody could explain them theoretically. Then in 1873, a young Dutch physicist named Johannes van der Waals had a brilliant insight. Van der Waals asked himself, how can we modify the ideal gas law to account for these two physical facts? His answer was ingenious. Van der Waals created a modified equation that includes correction terms for both molecular attractions and finite size. Here's the Van der Waals equation. Open parenthesis P plus A times N squared divided by V squared, close parenthesis, times open parenthesis V minus NB, close parenthesis, equals nRT. This looks complicated, but each term has a clear physical meaning. Let's break it down piece by piece. First, let's examine the pressure correction term. The corrected pressure equals the measured pressure P plus A times N squared divided by V squared. This is subtle. Why are we adding to the pressure? Think about what's happening at the molecular level. Molecules near the container wall feel an inward attractive force from all the other molecules behind them. This reduces the force they exert on the wall. So the pressure we measure is actually lower than the pressure the gas would exert if there were no intermolecular forces. We need to add a correction to account for this. The correction term is A times N squared divided by V squared. The parameter A depends on the strength of intermolecular attractions. Stronger attractions mean larger A. Why N squared over V squared? The number of attractive interactions is proportional to the number of molecule pairs, which scales as N squared, and the strength increases as molecules get closer, which happens as volume decreases. For nitrogen gas, the parameter A equals 1.39 atmospheres liters squared per mole squared. This value was determined from experimental data. Now let's look at the volume correction term. The free volume available to the molecules equals the total volume 5 minus NB. Here B represents the volume excluded by the molecules themselves. We subtract because the molecules themselves take up space. The actual free space available for movement is less than the container volume. The parameter B is the excluded volume per mole. It's related to the actual size of the molecules. The excluded volume B is approximately 4 times Avogadro's number times the volume of a single molecule. The factor of 4 comes from the geometry of sphere packing. For nitrogen gas, B equals 0.039 1 liters per mole. This seems small, but at high pressures when the total volume is small, NB becomes significant. Let's test the van der Waals equation with the numerical example and compare it to the ideal gas law. Suppose we have 2 moles of nitrogen gas at 300 Kelvin compressed into a 1-liter container. Calculate the pressure using both the ideal gas law and van der Waals equation. First, let's use the ideal gas law. P equals nRT divided by V. P equals 2 times 0.0821 times 300 divided by 1, which equals 49.3 atmospheres. This is the ideal prediction. Now let's use the van der Waals equation. Solving for P, we get P equals nRT divided by, open parenthesis, V minus NB, close parenthesis, minus AN squared divided by V squared. Substituting values, P equals 2 times 0.0821 times 300 divided by, open parenthesis, 1 minus 2 times 0.0391, close parenthesis, minus 1.39 times 4 divided by 1. This equals 49.3 divided by 0.922 minus 5.56, which equals 53.5 minus 5.56, giving us 47.9 atmospheres. So van der Waals predicts 47.9 atmospheres compared to 49.3 for the ideal law. The difference is about 3%. Notice the van der Waals pressure is lower. Why? Because at this moderate pressure, the attractive forces dominate. The attractive correction term of 5.56 atmospheres is larger than the volume correction. Now let's see what happens if we compress the same gas even more into just 0.1 liters. The ideal gas law predicts 493 atmospheres. Van der Waals gives 49.3 divided by, open parenthesis, 0.1 minus 0.0782, close parenthesis, minus 5.56 divided by 0.01. This equals 2,263 minus 556, giving us 1,707 atmospheres. Now we see a massive difference. Van der Waals predicts 1,707 atmospheres, while the ideal law predicts only 493. The ideal law is off by a factor of 3. At this extreme compression, the finite molecular volume becomes the dominant effect. The denominator 0.1 minus 0.0782 is very small, causing the pressure to skyrocket. The most remarkable achievement of the van der Waals equation is that it can predict phase transitions. It explains why gases condense into liquids. The equation predicts something called the critical temperature. Above this temperature, no amount of pressure can liquefy the gas. The critical temperature T sub C equals 8A divided by 27 RB. For nitrogen, this equals 8 times 1.39 divided by 27 times 0.0821 times 0.0391, which gives 128 Kelvin. The experimental critical temperature for nitrogen is 126 Kelvin. Van der Waals predicted 128 Kelvin without any knowledge of the liquid phase. This is remarkably accurate. The van der Waals equation revolutionized chemical engineering and has enormous practical applications. First, it's essential for industrial gas liquefaction. Companies that produce liquid nitrogen, liquid oxygen, or liquefied natural gas use van der Waals type equations to design their equipment. Second, it's critical for high-pressure chemical reactors. The Haber process for ammonia synthesis operates at 200 atmospheres. The ideal gas law would give completely wrong predictions. Third, the petroleum industry uses modified van der Waals equations to model oil and gas behavior in underground reservoirs where pressures reach hundreds of atmospheres. Fourth, atmospheric scientists use these equations to model real gas behavior in weather prediction and climate models, especially for water vapor condensation. While the van der Waals equation is much better than the ideal gas law, it's not perfect. Modern science has developed even more sophisticated equations. The van der Waals equation is typically accurate to within 5 to 10% for moderate conditions. That's good, but not good enough for precision engineering. Modern equations like Redlich-Kwong or Pang-Robinson are more accurate. They use temperature-dependent parameters and more complex correction terms. The most accurate approach is the virial equation, which expresses Z as a power series in pressure or density. But it requires many experimentally determined coefficients. Let me pose and answer some important conceptual questions about what we've learned. Question: why does intermolecular attraction make a gas easier to compress? Think about it for a moment. Answer: because the molecules are already pulling on each other, they want to get closer. When you apply external pressure, the intermolecular forces assist the compression. It's like having helpers pulling from the inside. Question: why does finite molecular size cause the gas to resist compression at high pressure? Answer: because molecules are physical objects that cannot overlap. When they're packed tightly, there's literally no more room. Compressing further would require deforming or crushing the molecules themselves, which requires enormous force. Question: at moderate pressures around 10 to 100 atmospheres, which effect typically dominates for most gases? Answer: attractive forces typically dominate at moderate pressure. This is why Z is usually less than 1 in this range. The molecules are close enough to attract, but not so close that their size matters. Question: is there a pressure where the two effects approximately cancel out? Answer: yes, at a special temperature called the Boyle temperature. At this temperature, the attractive and repulsive corrections nearly cancel over a wide pressure range, and the gas behaves almost ideally. Let's step back and appreciate the bigger scientific lesson here. The ideal gas law is a simple, elegant model that works beautifully under many conditions. But every model has its domain of validity. Recognizing when a model fails is just as important as knowing when it works. Engineers collected decades of data on gas behavior. They cataloged the deviations systematically. This careful empirical work was essential. Van der Waals succeeded because he understood the underlying physics. He didn't just fit a curve to data. He incorporated real physical mechanisms, molecular attraction and finite size, into his equation. The ultimate test of a theory is prediction. Van der Waals' equation predicted critical temperatures and phase transitions without being designed to do so. That's the hallmark of a truly great theory. Let me summarize the key concepts we've covered. The ideal gas law assumes molecules have zero volume and no intermolecular forces. These assumptions work at high temperature and low pressure. Real gases show dramatic deviations at high pressure or low temperature. They compress more easily than predicted, then suddenly resist compression. Van der Waals added two correction terms. The pressure correction accounts for intermolecular attractions. The volume correction accounts for finite molecular size. These simple corrections successfully predict complex phenomena, like critical points and phase transitions. Modern engineering uses even more sophisticated equations of state, but they're all built on Van der Waals' fundamental insights.